All right, so I didn't know what to call this one, so I called it proportional projectiles. This is just another type of look at a projectiles problem working symbolically. You're essentially going to derive an equation. You're going to reason proportionally, and so we're going to kind of go through a bunch of things with this one problem. So we're rolling a ball off a table. Tables are flat, that's important. We know the height of the table, and we know where it lands, and we know the speed with which it travels. So that's a lot of known information. The question is, in terms of this original distance, if we increase the height of the table to double its initial value and essentially repeated this experiment, how far would it go? And so hopefully it's obvious that if you use the same initial speed and you double the height of the table, then the ball's going to travel further. And that's basically because it's going to have this speed v for a constant for the entire time it's in the air. And by bringing it to a greater height, you just increase the amount of time it's going to spend in the air. So I'm going to go through like kind of full-blown analysis of this problem to show you the answer, and then maybe talk about how you could sort of game the question and get right to the answer. So the first thing I'm going to do is say I'm going to get some of these variables in here and put them with the letter D. So I'm going to analyze the horizontal motion of this projectile first. And so we have constant velocity motion. That distance D I have set up as x in my equation. I've also set up x naught to be 0. So really the distance is the velocity v times the amount of time it spends in the air. So we'll say that's like equation number 1 that I'm going to just kind of keep in my pocket for now. Now, the distance it travels depends on the velocity, which doesn't change, and it depends on the time it spends in the air. And because of this height of the table changing, the time is going to change. So I want to figure out like how the time is going to change and use that to kind of work backwards. So I'm going to start with the second part of the problem with this equation. And I'm doing it because I like, acceleration is constant, and there's something special about the beginning of this. So as far as this goes, a table is flat. And so the significance of a flat surface where something's being rolled off of it is that Vy naught, or the initial vertical component of the velocity, that's going to be 0. So that term disappears, and it's landing on the ground. And so y equals 0. So this simplifies to the following. 0 equals the height of the table is the initial position of the ball. So 0 equals h plus 1/2. And I'm going to do a type of substitution you haven't seen yet, but I know that the acceleration is negative 9.81. Now, I could put negative 9.81 in, but I never want you to do that unless you're getting me a number. And so what I want you to do is put in negative g for the acceleration due to gravity, because it's negative 9.81 meters per second squared, and that is times time squared. So it is possible to use just this work to figure things out, but I'm going to go kind of like all the way through this and derive an expression for d that is in terms of h and any other variables that show up. So I'm going to solve this. I'm going to subtract h from both sides. I get negative h equals negative 1/2 gt squared. And if I solve this for t, I get t equals the square root of 2h over g. And we'll call that equation 2 that I now have with me. So this is where you can really kind of finish the problem if you want, but again, I'm going to do more. We have the distance in terms of velocity and time, so initial velocity and time. And then we have time in terms of the height and little g. So, v is not going to change, little g is not going to change. The height is the thing that actually changes. And so that's important. And the proportionality in here is something I'll come back to. But the third thing I'm going to do is I'm going to combine equations 1 and 2. So I combine equation 1 and equation 2. And I say, okay, that means that d equals the initial velocity it has coming off of the ramp times time. I know that time is equal to the square root of 2h over g. So the distance is equal to v times the square root of 2h over g. Um, a separate question I did not ask was derive an equation for d in terms of v and h and any other fundamental constants, of which g is one of them. So here's an expression that you can use. You can really use this one or this one to figure things out. So as far as the proportional reasoning goes, this equation tells me that the distance traveled by this projectile is proportional to the square root of the height of the table. And basically that means however you change the height of the table, the effect of that on the distance it travels is the square root of that change. And so, if we think of this as the height of the table became twice the height, then the distance traveled is going to be root 2 times the original distance traveled. So whatever change you make in h, you get the square root of that is the change in d. Well, the square root of 2 times d would be an acceptable answer. If you wanted to get a number, you could maybe say 1.4d. And so your final answer is, just because you double the height of the table doesn't mean that you double the distance the projectile travels. It actually gets a smaller than that effect because of that proportionality. You get root 2 times the distance. It still increases, but it doesn't double. I just want to point out that you could have kind of done that as early as maybe here, but definitely here, and said, well, okay, if I double the height, the effect on time is square rooted. So doubling the height gives me square root of 2 times the time. And then if I have square root of 2 times the time, I also have square root of 2 times the distance because these two are directly proportional with no modification. So however the time of flight changes, the distance will change the exact same way. So that takes you through some symbolic work with projectile problems, deriving equations, and then working with proportionalities. And so hopefully that is helpful. Thanks.